Hello everybody, here's our video for lecture 2.3. But this is actually going to be two videos for this lecture. I'm going to talk about IR spectroscopy. This is part one, that's what this video is. And then we'll talk about the isomer flowchart and alkenes, different alkene isomers in part two. So that will be posted in a different link. So let's go ahead and start with IR spectroscopy. Now this is in chapter 13 of the book. It's a little bit adjacent to what we have been talking about so far, but the lecture requires some pictures and images, graphs, and so I posted skeleton notes on Blackboard. If you go to our Blackboard site and open up this link, it'll be available to you when you watch this video. You can download or print these skeleton notes, and that's what I'll be filling out in my sheet here. So I would do that before you continue on with this video. You can already see there's some text here, and so I typed that out instead of having you all write that in your notes. Now, if you prefer to write everything, totally fine. You're, of course, welcome to do that. Okay, so IR spectroscopy, this is something you'll come across in your organic lab courses and then in our course as well. And this is a method that scientists will use to study molecules. So if you generate something, you do a chemical reaction, produce a new molecule, we need to have methods to assess what that molecule is and if you've actually synthesized your target molecule. So this is one of the ways that we can study a molecule. And so some fundamental information will start here. Atoms in molecules are constantly in motion. They're constantly moving. We think about molecules as being stationary, about the atoms being stationary. That's how we represent them, because to represent motion is difficult. But in reality, atoms are constantly in motion. And there are, you may have caught a glimpse of this video, there are different ways that atoms move around in a molecule. So each of these different types of vibrations are shown on a model of a molecule. You'll see the green atoms, which are bonded to that black central atom, moving around. So I'll play this, and you can see those different types of vibrations that occur: stretching, rocking, twisting, wagging, and scissoring. So in these molecules, these atoms are moving around in different motions. These movements require energy, and atoms can absorb energy for those movements to occur. But different types of bonds exhibit different motions of different energies. So we'll say different vibrations exhibited by each type of bond. This could be like an OH bond, a carbon to carbon double bond, carbon to nitrogen bond, carbon to oxygen, etc. So this is just a list of some types of bonds. These happen at specific frequencies of light. So different bonds vibrate at different energies. But these are all within the infrared region of the electromagnetic spectrum. So your electromagnetic spectrum is shown here. This is all the different types of light, of energy. Lower energy is on the left. High energy is on the right in this spectrum here. Sometimes if you look it up, you'll see those flipped. The high energy will be on the left and the low will be on the right. But this very small portion here is the visible spectrum. So visible light is in that region. And then other types of light with higher and lower energies we cannot see, but there's still waves with those energies and in those regions. So the infrared light, notice it is right here, right to the left, just slightly lower energy than visible light, than red visible light. So that's our infrared. So infrared light can be absorbed by molecules, and that's the principle upon which IR spectroscopy is generated. So when IR light is shown on molecules, the bonds in that molecule will absorb the energy and vibrate. So if IR light of the specific frequency and energy of a specific bond that can absorb this light, is shown on that molecule will absorb that energy and vibrate in the ways that we saw in that video. So how this works practically in a lab is that there is some IR light source. Think of like a light bulb, but that light bulb is showing IR light. So we got energy coming from the source. This will shine light onto a molecule. That molecule will absorb some of that IR light, whatever the bonds in that molecule can absorb. And then whatever is not absorbed by that molecule is detected by a sensor or detector. And then the detector will produce some readout. What's noted in IR, we'll note this here, is that the sample, that molecule, is not destroyed. We don't have to break apart bonds to understand the bonds that are present. We're just shining some light on the molecule and then detecting what is not absorbed. So if there were, this is what a IR spectrum looks like without any information. So right here, this is our IR spectrum. The y-axis is percent transmission. So that's the transmission of the IR light that reaches the sensor. If there were no molecule present, then you'd have a constant 100% transmittance. So if no molecule, all light reaches the sensor. And then light energies on the spectrum are measured in wave numbers. In units of centimeter to the negative first power. This is equal to 1 over wavelength. Of that light, or 1 over lambda is how we, that's the symbol that we use for wavelength in chemistry and physics. So different wave numbers or wavelengths or different energies of light are in the IR spectrum are shown on the molecule. If there is no molecule, theoretically, all that light would reach the sensor and you'd have 100% transmittance. But if we have a molecule there, as long as that molecule has bonds that can absorb IR light, it'll absorb that light. So here's an example of a molecule. This is 2-propanol. That molecule was put onto an IR instrument. We call these devices that we use in chemistry that help us study molecules, we call them instruments. So that was put on an instrument, and this is the IR spectrum. I'll try to zoom in here a little bit more. That was the readout for 2-propanol. So this molecule, we have CH3, second carbon is bonded to an OH group, and then another CH3. Now we'll talk about where different frequencies are, but see how these are labeled on the spectrum. So if we talk first about this OH group, this broad peak here is characteristic of an OH bond. Let's draw out that bond here, actually. So the bond between oxygen and hydrogen here can absorb IR energy in about 3,500, a little bit less than 3,500 wave numbers. That energy it will absorb. And so the percent transmittance decreases at that point because of the OH group present in that molecule. Now, as I'm talking, I'm noticing that the y-axis here has a different label, and it's essentially the opposite of transmittance. So they say absorbance, percent absorbance. So I apologize if this is confusing. I think you'll mostly see transmittance. But what this is saying, notice that the top is 0. So that's saying the molecule did not absorb that energy. If it has a high absorbance, then the peak is lower, and that's what we see for that peak that I've highlighted in pink. But it looks the same if you either have 100 down here and 0 at the top for absorbance, or you have 0 at the bottom, 100 at the top for transmittance. Okay, so we've got the OH bond there. Another notable bond is that CH, so carbon to hydrogen bonds, are typically right around 3,000 wave numbers. So this one here represents the carbon to hydrogen bond, and that is all of the carbon to hydrogen bonds that are present in the molecule. I'm highlighting 1, but there are 7. Another characteristic peak is this carbon to oxygen peak here. That bond absorbs IR light at about 1,200 wave numbers. So that's this bond here. So each of these bonds, I'll highlight them in pink here. Absorb IR light. We'll say at specific wave numbers. That's what we're using to describe the energy. And so they show up as different peaks. Now you can see there are other peaks in the spectrum, and we'll talk about this in a moment. Some locations of peaks are more informative than others because, for example, lots of different types of bonds absorb energy in this region over here. And so it doesn't really help us distinguish what's present in a molecule because these peaks could correspond to a lot of different types of bonds. So there are characteristic peaks that we'll look for, and let's draw that right here. Characteristic IR absorption frequencies. So let's draw a general IR spectrum here. So this x-axis is wave number. In units of centimeters to the negative first power. And we will fill in the y or the x-axis. We'll start at about 400 wave numbers. Then let's go to 600. 1,000, 1,600. This is not drawn to scale. But we'll note those intervals here because they're helpful for certain bonds. Okay, so starting at the left, from 4,000 to about 2,500, in this area, OH bonds absorb energy, CH bonds absorb energy, and NH bonds absorb energy. And these are stretches. Oops. In the 2260 to 2100 area, our carbon to carbon triple bonds and carbon to nitrogen triple bonds are in that area. In 1800 to about 1400, which I didn't label, so we'll just make this one small. These are double bonds, so carbon to carbon double bond, carbon to oxygen double bond, carbon to nitrogen, or nitrogen to oxygen. Nitrogen to oxygen single bonds are in this overlapping area as well. Carbon to hydrogen bonds are here. So we notice in this area there's a lot of overlapping bonds. And then we'll add one more right here as well. This is carbon to oxygen single bond and carbon to nitrogen. If you're not exact, it's okay. We're going to have an IR table that's coming up in the notes that has specific regions. This is just to give you an idea. At very low wave numbers, carbon to hydrogen single bonds also absorb that energy, and carbon to carbon double bonds. Now, one thing you'll notice is not here are carbon to carbon single bonds, oxygen to oxygen single bonds, nitrogen to nitrogen single bonds. Those bonds don't absorb IR frequency. So we're looking at bonds either between two different atoms, or if it's the same atom, it's a double or a triple bond. All right, one more thing I want to note is between, or really just above, about 1,500. We'll draw it right here. And then higher wave numbers. We call this the functional group region. And this is where we'll focus most of the analysis, because this region has a lot more informative peaks than the other region, which we will call the fingerprint region, which is just approximately less than 1,500. I'm not saying that everything with wave numbers lower than 1,500 is not useful, but generally what's higher than 1,500 is useful. And this is referred to as the fingerprint region. And like I mentioned, there are a lot of overlapping peaks. I didn't draw all of them here, but a lot of overlapping peaks in this area that can make it hard to analyze. Okay, so the IR table organizes all of this nicely. It is uploaded to Blackboard in the handouts folder. And this is something you would be provided on assessments as well. So you want to learn how to use it. There are specific bonds that you'll see more frequently than others where you might start to remember where to look for those peaks. But let's look through this table and, like I said, use this as a reference guide. Sometimes peaks might not be in exactly the ranges that are listed here, but this can give you a guideline to know what to look for or where to look on an IR spectrum. So we saw for the 2-propanol example, if we just look at that OH peak, that was about 2,500. In this table here, notice that it is organized by bond type. So just two tables organized by bond type. Here we have the region where OH bonds would appear. And OHs are between generally 2,500 and 3,650. Knowing the difference between these not hydrogen bonded, and acids isn't needed at this time in our class. So you can look through this wide region here. We have carbon to hydrogen bonds. That's where we start in the table. But notice alkane, so all single bonds, alkene, double bonds, aromatic, we don't know what that means yet, or aldehyde, so you can ignore what those words mean, just include the ranges here. In alkyne, triple bonds have slightly different areas that they would show up. Carbon to oxygen, these are all different functional groups that are listed on that large list of functional groups that was a handout on Blackboard. But again, we haven't really seen these words before, so don't get too caught up in the jargon. Just look for the specific type of bond. So carbon to oxygen double bonds are right around 1,700. So let's put this to practice. Think about an example and how one might use IR spectra. So let's do this example. Let's say a researcher mixed up their vials of all 4 of these chemicals. So they have 4 vials. Each one has one of these chemicals, but the researcher doesn't know what is in which vial. So they take an IR spectrum of vial A, whatever they labeled as A, they don't remember what's in it, but this is the IR spectrum. From the IR spectrum, can we determine what molecule is in vial A? If we look at the first molecule here, there is a carbon to oxygen double bond. Carbon to oxygen double bonds, this is one specific peak that is useful to recognize if it's there or not in an IR spectrum. Carbon to oxygen double bonds are right around 1,700. Like I mentioned, all of these are in that 1,700 region. And then they also have this S after, and that indicates strong absorption. So you can see that real small at the bottom. So that means that the percent transmittance should be very low in those areas. If we look at about 1,700 here, we don't have a peak with a strong absorption. We have a short peak, but if we're looking for a carbon to oxygen double bond, that peak should be much lower, and we don't have that here. So it's probably not A, it's probably not C. One thing that we do notice, well, we have peaks right around here at about 2,500. That's a sharp peak. This corresponds to carbon to hydrogen bonds that I'm circling at the top there. So this indicates we have carbon to hydrogen bonds, but guess what? In all of these molecules, we have carbon to hydrogen bonds. So that peak is not very helpful for this problem. Another sharp peak that we have is right here, around 3,500. Going back up to our table and considering what our 2 options are, B and D. Carbon to oxygen single bonds are in this region, not at 3,500. And that's present in B. We also have that in D, but another peak we have in D is that oxygen to hydrogen single bond. And oxygen to hydrogen single bonds are right in this region around 3,500. And that is what appears here. So this is an oxygen to hydrogen single bond peak. So with this IR spectrum, we can tell that molecule D is in this vial because the peaks that show up in the spectrum align with the bonds that are present in D. Another way or another type of question you might see with IR is, let's say you're given molecule A and you might be asked, where would you expect peaks for this molecule? For molecule A, we have carbon to oxygen double bond, so we'd expect a peak around 1700. We have carbon to hydrogen single bonds in alkane change, so we'd expect a peak here. And that's it. Those are the types of bonds that are present, so we'd expect those 2 peaks for that molecule, for example. So you'll see different types of IR questions. All right, so I'll end part 1 here, and then the next video I'll continue part 2, where we'll talk more about different types of isomers.